Hi, everyone. We've set up this Being an Engineer podcast as an industry knowledge repository, if you will. We hope it'll be a tool where engineers can learn about and connect with other companies, technologies, people, resources, and opportunities. So make some connections and enjoy the show.
It is so true that if students and if faculty, if we are not curious, it just sets us up to do work that does not excite us. If it doesn't excite us, it's not going to excite anyone else.
Hello and welcome to another wonderful episode of the Being an Engineer podcast. Today we're speaking with Dhruv Bhate. Dhruv holds bachelor's and master's degrees as well as a PhD in mechanical engineering and is currently the program chair at Arizona State University for their manufacturing engineering program. Dhruv has extensive experience in additive manufacturing as well as in bio-inspired design, both of which we will talk about today. Dhruv, thank you so much for being on the show today.
Oh, thank you for having me.
All right. So what made you decide to become an engineer?
I think the immediate, I come from India, and that's where I went, got most of my schooling in a town called Pune, in a state called Maharashtra. And while I was there, you're typically, as a child, when you're being raised, you have one of two options, medicine or engineering. And I sort of fell into that narrative that I would become an engineer by the process of elimination. However, the immediate spark for me was Formula One. It was the mid-90s. Formula One was in the news. We finally got to watch it on cable television. And I was just amazed that this was a sport unlike any other, where the engineering was arguably more important than the human performance. And I was like, that's what I want to do. I want to be a Formula One mechanic or be part of a team that builds and races cars. Now, I guess we talk about this as we go along, but that's not what happened with me. But that was that part that led me to say, I'm going to do engineering, and I'm going to do mechanical engineering because I want to build and race cars. That's
very cool. Nice. I love that. Who doesn't love a good Formula One race, right? Getting in back of a fast car. I don't know a lot about India, and I thought it was really interesting that you mentioned there was kind of one of two options that you had to choose from, medicine or engineering. Tell me a little bit more about that. How did that become kind of like the de facto two options for folks growing up in India?
It's a complicated issue, and I can't pretend to understand all of it. It's culture, a lot of it is culture, but a lot of it is also associated with, there are other paths, of course. There is commerce, there is the arts, etc. But the general assumption was that if you were doing well in mathematics and science in school, that those were the two options that were most appropriate for you. So my brother did engineering. Everybody around me that was good in their academic programs did engineering or medicine. And I think ultimately it's tied to the earning potential that those jobs had. We're talking about India in the 90s, which was a very different country than it is today. It was much more closed off to the world in the the leave alone thinking about making a job, making a career out of being a digital YouTuber and all, which is happening a lot in India these days. Those were just not even in our conception at the time. So if you wanted to make money, if you wanted to live a good quality life, those were your two paths forward. And a lot of parents, including mine, had an eye towards potential immigration for us to another country, typically US, but also England, Australia. And it was well known that to maximize your odds of migration, you want to work in a STEM relevant field. Those are the fields that you had the highest odds of, getting a chance to go abroad and potentially, if you so chose, build a life there. So it was a bit of both, or all three of these. Lastly, there's a lot of prestige associated with being an engineer or a doctor, the perception in India of the 90s was that those are the highest value providing professions. And so that was woven in there too. So more psychoanalysis than you asked for. But
No, that's super interesting. No, I find that really interesting. How about law? Is law a prestigious path there, or is it just not many people do become lawyers, attorneys?
In the 90s, I would say it was not, because so much of our education was based on science and mathematics. If you did well in those subjects, unlike in the US, you actually make a choice in the middle of your high school in India after 10th grade. You can actually start dropping subjects that you're not interested in pursuing more. So I dropped biology, for example, and people can drop mathematics too if they don't want to pursue it beyond 10th grade, and they don't learn calculus. For me, in those times, I guess law was always a couple of rungs lower, and it didn't help that I was not interested by it or intrigued by it. We didn't have a culture of television programs with lawyers and attorneys and CIS or Law and Order. We just did not have that in the popular psyche. So if you did not get to be a doctor and engineer, then you typically went into these other professions. Things have changed a lot. My friend told me that one of the most prestigious colleges in India, the last student that got into the arts program actually had scored higher than the last student that got into the engineering program. So it was harder to go study arts now than it is engineering.
Interesting.
But this is, 30 years ago, things were very...
Yeah. It's super interesting to hear that engineering and medicine were like the two really prestigious paths, right? Because here it's kind of like law and medicine are the two most prestigious, I guess, professions, right? And engineering, like no one's going to look down on an engineering degree for sure, but it's not like at the same level in the US. I don't know. It's just interesting how different cultures have different ways of looking at it. So, all right, well, let's get into the engineering stuff now. You did quite a bit of additive manufacturing towards the beginning of your career. How did you get into that? And did it have anything to do with Formula One race cars?
It did not actually. I stumbled onto 3D printing and additive manufacturing when I was working at Intel. Somebody at Intel, I was working at Intel in a microelectronics packaging assembly floor, and I had several different machine tools and operations that I was in charge of at different times. And during that time, there was one piece of equipment which had a pick and place head. It would pick up little chips and transfer them from one tray into another tray. And that head had to be ESD safe. And it was proving very difficult to get that head from the supplier. So that's when I learned that we got some new heads and that they were 3D printed. This is around 2013 or so, about 10 years ago. And that got me intrigued where they came from. And I went down and I looked at it. It was a Stratasys FDM machine. And there was a completely different group of people. They were a support organization, the manufacturing floor, started with, fabricating tooling for us. So I got to know them. That was my first intro to additive manufacturing. But then I happened to visit there's an organization called IEEE, Institute of Electronics Engineers, and they host a monthly seminar in Phoenix, different chapters all over the country. I attended the Phoenix chapter for a talk on additive manufacturing. It's around 2014 or so. And it was by this guy at a company called PADT. And I walked up to him after the talk, and I just fell in love with the sheer prototypes and their complexity and the color that he had brought with him, you know. And I walked up to that table and I said, my sabbatical is coming up. Intel gives you a sabbatical every 7 years in those days. You could take 2 months off. Can I come and spend those 2 months at PADT and intern there, free internship? And I just want to learn, you know, and put me on your tools. I want to 3% on all the machines that I can get my hands on. So it began accidentally. And then I attended this seminar because I was intrigued. And I think the third one that topped it off was Netflix had a documentary around that time called Print the Legend, which talked about, the making of MakerBot and Formlabs and how these two startups, had to take it from the big guys, Stratasys and 3D Systems at that time. And the three things together just convinced me that if there was an opportunity for me to get into this field, I wanted to embrace it. You know, one thing throughout my engineering education and my time at Intel, I was being a good engineer, you know, and I was solving problems. I was doing things that needed doing, but I never felt like I was in love with an idea, a topic, a theme, a subject. But additive manufacturing, for some reason, when I saw these structures, I just literally, the first time I felt truly in love with something, maybe since my Formula One, which was a more childlike appreciation for engineering. But now I finally said, wow, here's a technology that you can really maximize for its time potential. And and by then I was an engineer, so I kind of had a more nuanced understanding of manufacturing, design, process development, and additive was this huge burgeoning field with so much potential that I felt I just had to get into it. So I actually did that internship at PADT. I went back to Intel. I worked for another month, but I essentially resigned and I joined PADT full time. Because that's how excited I was about technology. And I'm very glad I did that. It was the first move that I made in my career that was tied to, a technology as opposed to a company.
That's a great story. Thank you for sharing that. Yeah, I know the guys at PADT. They're wonderful people there and very good at 3D printing for sure.
Yes.
What are a couple of ways that engineers should be using 3D printing that maybe they aren't even aware of right now?
Because I'm now in a research world, I tend to think of these questions more from an academic perspective. So let me give you that standpoint, which often means that what I'm about to say is not ready for prime time. It is. So my first and most interesting use case of additive, which I think is already appreciated by many, but may not be as prevalent in industry yet, commercial application, is sort of the marriage between these so-called meta materials or architected materials and bio-inspired design. I think people do them separately, but to me, the place where they come together is when you put these two ideas together. That's when much more innovation than when we tackle them independently available, and so that is my first area. If you can look at natural structure that is architect, in other words, is discretized into small structures like cells, like in a honeycomb, but more than just that, people have 3D printed armor like scales. People have 3D printed hair-like structures to trap moisture. Those kinds of applications where you look at additive as for its potential to create discrete, repeating structural elements, and then look at how nature is using those elements, how they are designed for what particular functions. That's one untapped opportunity I see. Maybe more academic right now, but I think there are opportunities in the industry well for it. The second one that I think we're all struggling with, me included, is really taking multi-material additive to its potential. Yeah, I don't think it's found a killer application yet. I don't think it's solved a lot of problems about the process itself, what happens at the interface. This could be functionally graded materials, like how we transition from one alloy to another. So that is another area that I think the academic side, there are lots of opportunities, and we're not probably doing as much as we ought to be doing. That's my quick answer to those two.
Okay. So you are an academician now. You've kind of transitioned from industry to a career in education. What were some of the lessons that you learned when you made that transition?
There were quite a few. I think the biggest, these lessons stem from challenges. So there are many positives to coming from industry and going into academia. You bring a lot of experiences, in particular with project management, with execution, that I don't think most academics have. So there are lots of advantages, but the biggest challenge and the lesson associated with that challenge was that, any academic career, at the crux of it, when done right, is really about identifying research questions, about applying the scientific method to work, as opposed to thinking of your work as a project. I was telling, I teach a class here this summer. I'm teaching it for the first time. It's called Principles of Independent Research. And one of the discussions that I'm trying to get the students into is, what is the difference between a project and research? Because there are some differences. And I think when I came from industry, I was still thinking with too much of a project mindset, that you're trying to achieve a certain outcome in a certain amount of time, and you have to break it up into objectives and tasks and execute that. And that's great. You get your job done. The sponsor who gave you the money is very happy. But when you go to write that up, a paper, it is very hard to tell a narrative that is really emphasizing the generation of new knowledge, So that's been my one big lesson. My first lesson is that research is different from the execution of projects that many engineers do so well. It cannot be often broken up into, time specific deliverables and tasks. It depends on the definition of a well-posed research question and the development of well-posed hypotheses. So that was lesson number one. Lesson number two was just, you need patience and time to build up an academic community. You've spent a lot of time in one company or two companies, and most of your contacts in an organization, in an industrial organization, are your peers, your management, and your customers, and occasional other stakeholders. Here, your community is the people that are doing similar work to you, and they could be in another continent, they could be across the hallway, and that building that community of peers who you're going to learn from, who are going to, at different stages of your career, assess your performance, is a second lesson that I did not, take seriously initially. This means going to conferences, giving invited talks, inviting other people to your, to your university to give a talk. These are not things that we do in industry at all. We just are very focused on solving problems, developing ideas. We're not really thinking about building a community, often for some intangible gain down the road. So those are just two of many lessons that I've learned that maybe took me 4 or 5 years to truly grasp, and truly appreciate. And now I'm trying to pass down these lessons to my students as well. I like to tell my students that there are 3 C's of research. And I don't know if I've come up with this or if I've picked this up from someone else, but and these 3's are often not as critical in an industrial environment. They are, but I don't think they're as important. There are some other things that are more critical. And those are curiosity, right? I mean, we really value that, and it sounds like I'm paying lip service to a cliche, but it is so true that if students and if faculty, if we are not curious, it just sets us up to do work that does not excite us. If it doesn't excite us, it's not going to excite anyone else. And then the second C is creativity. You have to take that curiosity. It's sort of the fuel. The creativity is the engine that converts that fuel into a motive power that can do things. And then the last C is connection. You need to be connected, be it on the internet, be it at conferences, be it through journals. And we ultimately rely on so many connections to people, organizations, entities that allow us to take that fuel, that engine, and actually build a car so we can get somewhere. So those are some of that's a little philosophical lesson that I've learned. But it took me some time. I think the biggest thing is you cannot construct a research problem, a research task, a research endeavor the same way you craft a project. That's taken me some time to learn.
Yeah. I like your 3 C's a lot. In fact, we hear on the podcast, I'm always asking people, what do the best engineers have in common? And curiosity, creativity, those things come up a lot. And I might add a 4th C, communication. That one is like all the time. Everyone is talking about, oh yeah, you need to be a good communicator, which I think us who have been in the industry for a while kind of get, but maybe newer students or new graduates don't fully appreciate the importance of being able to communicate with other people. Well, let me take a real short break here and share with the listeners that teampipeline.us is where you can learn more about how we help medical device and other product engineering or manufacturing teams develop turnkey equipment, custom fixtures, and automated machines to characterize, inspect, assemble, manufacture, and perform verification testing on your devices. I read that little promo ad every time I do a podcast, and I wonder how many people just hit the skip 30 seconds forward button whenever I read that. They're just waiting for it. Teampipeline.us is where, okay, 30 seconds, skip ahead. All right, now we're back into the good stuff here. I should come up with something really different, something that's like 4 seconds, so if they skip ahead 30 seconds, they're going to miss 26 seconds of really good stuff. All right, that's my new goal. I need to come up with a 4-second promo ad here. All right, back into the questions here. Biomimicry, that's something that you work a lot in. What is biomimicry, and how can it help engineers who are developing new products as opposed to only research and academia?
So I think the many definitions of biomimicry, the one I like is the one that's often described by the mother of biomimicry, Anine Benyus, who wrote a book in the 90s. And she essentially calls it any kind of innovation that is inspired by nature's genius, right? So that's sort of a very broad description of the subject. The biomimicry generally can involve what aspect of nature's genius are you inspired by? Generally speaking, it could be either something to do with the shape and the form of nature. So like the shape of a bird's beak. That was what people call bio-inspired design. And that's the specific aspect of biomimicry that I work on. People are also trying to synthesize materials, at a chemical level that are inspired by natural materials. People are also trying to develop systems, drones communicating with each other the way ants communicate, for example. So typically it's forms, materials. People are also working on processes. Can we create manufacturing processes like self-assembly that mimic biological processes? So what I really focus on is bio-inspired design. And there the idea is to ask the question, on one level, why does nature have the shapes she does? Why are trees shaped the way they are? And the beauty of asking those kinds of questions is there's an infinite number of them. You never run out. But what does it mean from an engineering standpoint? It's that a lot. If you sort of break down how we all learned design and the interaction of design with mechanics on the one hand, or let's say behavior, the environment, stresses, like, fatigue. We got to design to meet those requirements, and we also got to design to be manufacturable, right? So in some sense, nature is doing the same thing. Nature has a certain list of materials available. There's a developmental process that leads to a certain design, and that design, has to withstand a test in an environment, in ecology. And if it's a good design, it's going to get selected and improved on through the processes of natural selection. So the parallel is great. So lots on the academic side. What does it mean for a practicing engineer? I think this is one of those untapped mines of ideation. In fact, it is just mind-boggling to me. If you take the honeycomb and you look at the number of products, you do a pattern search for honeycomb. Yeah, that one idea that if I want to minimize material and still divide area into equal cells of the same area, the most efficient way to do it is with the hexagonal honeycomb. There'll probably be hundreds of patents that are exploiting honeycomb shapes for different things, from sandwich panels to filters to sound absorbers. I'm sure that's just one organism's one creation, right? So that we recently submitted, and it's a patent pending idea on taking lattices that were inspired by a sea sponge. There is the sea sponge that lives in the ocean and constructs an exoskeleton using silica that it pulls from the water. And when you look at that sea sponge, it looks like a lattice grid. But when you look at it under a CT scanner and look it up real close, it's actually a mix of some lattice beams that are connected, they are welded together, and others that are woven, that are going up and down. So we said, why is it doing that? Why is it not woven everywhere or not connected everywhere? And voila, we studied that. We found it really helps with structural compliance. You can make very squishy lattices better than anything that has been reported in the literature. So we published a paper. We submitted a patent that is now being filed and patent pending on this one simple idea that we borrowed from natural observation. So I think, there's this amazing book that a guy named Stephen Johnson wrote. It's called Where Do Good Ideas Come From? Or Where Good Ideas Come From? And there are different, there are like 7 or 8 different sources that one gets good ideas from, and nature is one of them in that category. And I think that is the ultimate innovation. So let's say you're trying to solve a particular problem, and the biomimicry methodology, that folks teach goes into this. You have a particular problem that you're trying to solve. Maybe you're trying to make, a lightweight structure that can dissipate heat, because you've been asked to create a lightweight heat exchanger. You immediately go to nature and you say, where are thermal management problems found? What are some of the exemplars who solve thermal management problems while managing lightweight or keeping the weight of the entire structure light? And you find so many different examples. The beak of a toucan, for example, is one example where the beak is constructed of open cell foam and regulates the temperature of the entire toucan organism. And there's a beautiful website called asknature.org. I'm not affiliated with it or anything, but I use that a lot to go in and say, give me examples of this. Of course, these days with generative AI tools, we have other ways to search as well. But Ask Nature does a very good job of synthesizing biological exemplars for specific functions that you might be interested in. And that might lead you down a different design idea that you would not have gotten to without that. So that's how I think you can generate ideas. I do think that there is a big jump from saying it works like that in nature, and I've been able to extract it and show it as an isolated idea, maybe in a lab setting or in a computer simulation, to integrating that into the product where there might be additional requirements that the natural structure does not have to deal with. So I'm not suggesting that biomimicry solves all your problems, but it gives you an opportunity to create individual ideas. And then your next step is how do you weave them together into a product solution? That is much harder. We don't really work on that as much. We tend to evaluate individual ideas, try and generalize them up to a point, and then put our work out there.
Yeah, I've never heard of this asknature.org. That sounds really interesting. I'm going to take a look at that, and I'll put that in the show notes as well for all of the rest of you who would like to check it out too. In addition to asknature.org, where else can engineers go to get a sense for what research has already been done in regards to biomimicry and just getting ideas for how they might incorporate biomimicry into their designs? I know you and your colleagues have written a lot of papers on this, right? So there's literature out there. I think most companies don't have subscriptions to white papers, which makes it kind of hard to access. I mean, you could probably go to the library, I think, where typically community libraries do have subscriptions, but like realistically, how many engineers are going to go to their public library? Even though it's not that hard, probably not that many. So is there a good way to find this literature? And is it more than just white papers? How else can engineers find ideas in biomimicry that they can apply to their projects?
I think, generative AI and chat has become enormously useful. And if you had asked me this question 2 weeks ago, I would not have given you the answer I'm about to give you. But there is an amazing platform that I've just discovered called elicit.org, ELICIT, not illicit. I tell my, not like, but elicit, ELICIT.org. And it is like ChatGPT, it's a generative AI chatbot, but it only references published literature. So,
interesting.
And it summarizes the top 4 papers from a relevant standpoint. So it gives you an abstract summary for the question you ask. And it lists a bunch of papers. You can even check and say, only show me ones where the PDF is available. So it'll only show you those where it is in the open access domain. Increasingly, papers and journals and institutions are moving to an open access model and away from a subscription model. If you want a paper that was in the 70s, 80s, it's probably still behind the paywall. But otherwise, a lot of recent literature, the last 5 years in particular, is increasingly available open access. And so that is one option. If you are diving deeper, and when I was at PADT, I went to my manager, one of the principals of the company, and I said, can I get access to this website called Deep Dive, DEEPDYVE, not DIVYVE. Deep Dive is a subscription service. I don't know how much it costs at the moment. It was $40 a month back in the day. And it basically has access to not everything out there, but a lot of journals. They have a special subscription service for folks who are not affiliated with university that go about getting subscription. But I think elicit.org, not just for biomimicry, for any kind of research, is just fantastic. And there's probably going to be competitors and solutions coming up pretty soon. One wonders how they're able to source this information and how the rights are being handled and whether they will be around, 2-3 years from now. But at the moment, that is my hot tip, as they say.
That's an awesome one. I can't wait to check that out. I mean, that's one of the things that frustrates me is sometimes I'll search for some topic on Google, right? And there'll be a bunch of results, but they're all leading to some journal article that I don't have access to. So I can read like a short abstract, but I can't really read all the results and the conclusions and things like that. So elicit.org, that is super cool. I can't wait to take a look at that. Great pro tip. Thank you. Let's see. What advice do you have for students who might be interested in research careers?
I think I some of it I already addressed, like the lessons that I learned coming from an industry environment into an academic environment was really to truly understand what research means, and make sure that's what you want to do. And to me, as engineers, we do not get trained as much in the scientific method, and we don't truly appreciate, the value of those C's. And yes, I probably should call it the 4 C's now, throwing communication there. But I will say one of the things that takes my students by surprise is, a lot of times I actually tell them this, that I get disappointed that they are not as curious and enthusiastic about their research as they ought to be. I don't understand why this is the case. You have a once in a lifetime opportunity, you're doing your PhD, for example, to work with an expert, in this domain, have access to university facilities, including papers, journals, a library, equipment, materials. If you need a question answered from a different professor, they are down the hallway. You get to go to conferences. You get to do some pretty cool work and control your learning along the lines that you are interested in. So my first suggestion is, don't pick a topic. Be very cognizant of the topic you are picking, and make sure it's something that you feel a gut like for. If you view a PhD as just another job, I think it's going to be suboptimal always. So be careful with picking a topic. Be careful with picking an advisor. And I guess, there's a long list, but one other thing that I think surprises a lot of students is they don't appreciate how much reading and writing a PhD student has to do. I estimated for them that the average PhD publishes about 100,000 words. Yeah. And between their doctoral thesis, between, 3 journal papers and maybe 1 or 2 conference publications, that comes to about 100,000 words. And a PhD, a typical engineering PhD, is about 4 years long. And your first year, you barely write anything, traditionally. But you've got 3 years, that's about 1,000 days to write 100,000 words. That's 100 words a day. That's your final output, leave alone revision, editing, etc. So that comes as a shock to them. And then each paper cites at least 30 to 50 other papers that you have presumably read and that you are citing in your work. And each, so now you've got something on the order of 3 million words that you got to read during your PhD, which is like 3,000 words a week, So I think that last calculation is a bit wrong, but it basically boils down to 1 paper a week at a minimum over 4 years. So, if you can't even imagine this habit, developing a daily habit of reading and writing being part of your makeup for at least 3 long years, and you don't have a topic that really excites you, don't get into it. But if you do, and you do love to play with ideas, with thoughts, and also get your hands dirty, an engineering PhD is fantastic because unlike a lot of other PhDs, there are good job prospects after that. You don't have to go into academia. In fact, the majority of PhDs do not go into academia. About 85% of them go into industry. So the outcomes after a PhD are great as well. But you do need to find something you love, and you do need to be aware that that at the end of the day, the way our output is not a device, it's not a product, it's new knowledge. And the way we share that, the deliverable, is publication. And you have to make peace with that, or it's going to be a tough road.
Yeah, I'll chime in on the writing part, especially. Even in industry, it's really important to have good technical writing skills. And I noticed that a lot of engineers don't have good technical writing skills. Grammar is poor, spelling is poor, and just overall sentence structure and kind of the thought or the logic behind the architecture of the writing is not that great. And Can you be a good engineer and not have great writing skills? Yes, you can, but it's going to limit you. Like, it really, truly does limit how far you can go. I won't name any names here, but I can think of a few engineers I know who there are things that I won't ask them to do because they involve a lot of writing, and I know that it's not going to turn out great. And if they could do those things, they would be more valuable to the company, to whoever your employer is. So developing those technical writing skills, it might not be the most glamorous thing, but it really is important. And as engineering students and young engineers, you should definitely spend some time developing that skill.
Yep, I agree.
All right, I think we'll do one more question here, and then we'll wrap things up. Specifically within the context of your role as an engineer, what is one thing that frustrates you, and conversely, one thing that brings you joy?
I think one thing that has frustrated me at different times as an engineer, in my 10 years in industry and my 6 odd years that I've spent in academia now, has been this interplay between the engineering and the perception of your success within an organization, and how hard it sometimes is to enjoy the former because it is so tightly woven with notions of success. And what you need to do to impress a manager above, and how you need to present your work. I wish at times that we could just get lost in a subject for its own sake, And one of the reasons I joined Intel is because it is an amazing company at putting data and insight above all else. It did not matter who was presenting in a conference room. What mattered was our attempt to try and get at some truths that will allow us to move forward with some objective. So whenever that would get threatened by management or by politics or by perception, that used to frustrate me. In academia, it tends to take on a guise of administration. You get asked to serve on some committees. You get nudged into positions that maybe you don't want to do. And you spend a lot of time doing that instead of doing what you love doing, which is to answer your question, the second part of your question. What gives me most joy is, and I've taken me, this much time to sort of find it in academia, is the marriage of science and engineering, and I think the beauty of science is that it gets away with saying that the point of my work is to answer a question. What you do with that answer is another question, but I'm not going to conflate my answering of this question with anything else at the moment. The question is its own, point. Whereas engineers are much more focused on solving a particular problem. Even if we don't understand questions, we don't even ask questions many times. The way scientists write them down and articulate them and make sure they have hypotheses. I would probably not be happy in an entirely scientific domain, or, as I'm discovering, in an entirely engineering domain. But it's when you put them together, and ask an interesting question, find the answer to that question, and then bring it to bear some use. And you have the time and the space to do that without the pressures that are often present in industry or high-pressure projects. That is what brings me the most joy when that works well. They're part of it, and they get to see the joy, and we all share that. I don't know if you watched the movie Into the Wild, but at the end, there's a little spoiler, but the lead protagonist writes in a book that happiness is only real when it is shared. So that is after going on a journey of self-discovery, which is all about himself, he finds that he can feel happy, but it's not truly happiness unless there's someone to share it with. So I think to share these kinds of moments with students is definitely the thing that gives the most joy.
Well said. Yeah, we talk about joy here at Pipeline. The purpose of Pipeline is to promote joy in the lives of our team members. And so I've thought a lot myself about what is joy, where does it come from, and I think where I've ended up is joy comes from other people, right? Without other people, it's really hard to find true joy. I think joy comes from doing hard things with people that we care about. So right along what you're saying, definitely in alignment there. Well, Dhruv, thank you so much for spending some time with us today and sharing a little bit about your background and some pro tips and some insights. This has been great. How can people get in touch with you?
Thanks, Aaron. I've enjoyed all of this entire chat. People can get in touch with me on LinkedIn. That is the social media website that I'm most active on. Or they can visit our lab's research page. The group that I manage of about 10 students at any given time we call ourselves 3DX Research. So you can go to www.3dxresearch.com.
Wonderful. Well, Dhruv, thank you again for being on the show. Really appreciate it.
Sweet. Thanks, Aaron. Thanks for having me.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.